So if you go to lectures, all the information is on that page. So we have a session today, and we have a homework again, which will be task 03, which will be obligatory, similar to task 01. This one, though, is without AI, so you actually have to do some things at home. And then next week, we also have an oblig. So we're going to have two obligs in a row. But because all those obligs are about Haskell and about something new to you, I thought that this one will have 2 weeks and this one will have 2 weeks. So we will have sort of homework spanning 2 weeks instead of 1 week. But you will have to do those two homeworks and submit them. And after that, we will have a couple of labs with no obligatory work. And then it's up to you whether you're going to do it or not. So you don't have to do all the tasks in the course. You can pick which ones you want to do and which ones you don't. But oblig tasks, everybody has to do. And then some of the tasks, so if you go, for example, to this one, it will say whether there will or will not be peer review. So together with tasks and the obligatory work that you have to do, and the tasks that we do in school, we will also have peer review. Peer review will be always done at home, and we will have 1 or 2 weeks to do peer review, and then people who submit a particular task will participate in peer review, and people who didn't submit will not, okay? So then you can also prioritize. If you don't want to do a task, you can probably better skip the tasks which don't have peer review, because then you're not making yourself out of the peer review. So if you didn't do a task, it does not make sense to participate in the peer review. So you kind of have to do the task. Do you have to do all the tasks completely? No. So the idea is that you should always submit how far you got. So sometimes you can finish the task perfectly and it's like completely done. But sometimes you started and you got stuck. Then it's okay to submit kind of work that is not fully completed and then peer review it and then participate in peer review. Maybe you will see how other people approach the task and so on. So you will learn. So I encourage everybody to kind of work on the tasks and submit them. But we will have quite a lot of tasks and they are not hard, but they still consume some time. And then you may need to prioritize other subjects and so on. So you have to sort of play. But you can use this one as an indication of whether you should or should not do a task which is not obligatory. If the task is obligatory, you have to do it. It's part of the obligatory work and you have to do it. Again, you don't have to completely do it. You don't have to completely solve it, but you have to submit into the personal workspace. We do have some guideline about AI. So some of the tasks, I really ask you to use AI, generate everything with AI and do AI work for you. And for some tasks, I want you to type. And the typing thing is like training a muscle memory and so on. I can ask AI to do certain things for me, but I still kind of want to type stuff because that refreshes your memory and refreshes some of the commands, syntax, and how things work. So it's kind of useful to do it by hand. And yeah, we will have some tasks where we want to do it by hand. Later on, we will have more complex and more complicated tasks. And for those, we will be heavily using AI and we will be only guiding AI and fixing the things manually if AI gets it wrong. But for the early ones, they are so trivial that you should not use AI for it because they are so trivial, designed for us to practice, to kind of do them by hand. So the ones which is for this week and for next week, try not to use AI. What if you need syntax? So if you say, oh yeah, how I do this, like how is the struct syntax in Golang, okay? Then of course you can use AI. Instead of Googling for it or like searching on internet, you can just ask AI to show you how is the syntax for something, right? So you can say, what is the struct syntax or record syntax in Haskell, okay? And that's fine. And then you sort of type it yourself, whatever is needed. But try not to make it generate code for you. Like use it only to give you hints and give you syntax, and then you type it, so then you memorize it. By typing it, you will sort of memorize it. So just to give you a little bit of a flavor, we had, so let's say we had spent the task 00 on some command line stuff. And command line is important, and we will continue using it. And we will do things in command line more after those 2 or 3 weeks dedicated to Haskell. But I wanted to show you a little bit what I kind of expect from you at the end of the course. So I'm heavily encouraging you to use command line, and also personalize it and kind of make it kind of useful for you. So I'm using a fish shell. We will talk about it in 2 weeks, how to sort of make it a little bit better. So then if you personalize it, you will see, for example, that if I go to projects and I go to some sort of, let's go to our course. I go to 2026, right? So that's my Git repository of the course. I have some personalization, so I see which folder I am in. I can see what is the current branch I am in, and I can see if I have some commits to commit and so on. So it kind of gives me some extra information, right? So it is kind of useful. And then so let's go back home. So one of the things we had spent a little bit of time on is Oak and some of the basic command line things. So for example, we know how to list files in my home directory, right? How to clear the console, and we also know how to do some basic Oak scripts. So if I go, let's go back to the projects and go, let's see what we have here. So I have a bunch of folders, and then I have one README file, right? And the README file is 76 bytes, and I may have more files, and then I may want to ask, okay, what is the total sum of all the files in the current folder? And then I know I could write a program to read the current directory, check the file sizes and so on. But I also know the pipe operator, and I know ls, and I know that ls gives me the size, and I can see that it has like 1, 2, 3, 4, fifth column is the size. So I can write like a very simple pipe. So I can say, go over all the folders that I have, files that I have in the current folder, and oak it. And then oak uses space as a delimiter automatically, so I don't have to say what the delimiter is. If I had to say it, I would say, okay, the delimiter is comma or something, but because it is a space, I don't have to say anything. And then I have to say, okay, the first line I have to ignore, so I have to say nr is bigger than 1. And then I want to list the sum of all the files of the column 5, right? So I could say, okay, for every row, do sum plus equals 5, and then at the end print the sum, right? So I kind of like in 20 seconds I wrote like a simple script which makes me a sum of all those numbers which are here in the 5th column. I don't have to write any program, I don't have to do anything, and I'm using 2 small tools, one which is the ls and one which is this one. If I were to say I don't want all the files, I only want the files that don't have D in front of the first line, I can add an extra pattern at the beginning of this Oak pattern matching here. Instead of just saying ignore the first line, I can also say ignore the first line and ignore, so if the line does not start, if the line, shit, where is my That's the weird character. This one. If the line does not have, and then there is a regular expression. You're gonna spend a little bit of time on the regular expressions in the cloud course, but regular expressions are super powerful and very useful in many cases. So this basically, those two slashes say there is a regular expression inside, and then I say the line starts with D, right? So this regular expression matches every line which starts with D, and this one says don't, like it's not. So the whole line does not start with D, right? And then I have 76. If I want to say, okay, count me all the directories, I would say all like line pattern matching and then regular expression. Should you learn it? Yes, I think you should learn it. And will it be in the exam? Yes, it will be in the exam because it's so powerful and it will be kind of useful for you to know it for many different use cases where you have to do stuff with data. So ls is just one simple case here, but you might be getting something from a REST API and you need to check if it is correct. You might be checking your log files, and the log files is a lot of like well-organized data. So using this sort of a powerful mechanisms in the command line are kind of super useful, and you should learn it. Should you know it already? Of course not. And how hard it is? It is not that hard. If you practice it like few times, then it like becomes your second nature. So it suddenly you sort of see, oh yeah, I can do it this way. The most important thing here is this pipe, that I can pipe things through different programs and do transformations, because this concept is kind of super useful across all different categories of us thinking about problems, that we almost always use it. So if I'm defining a function, it produces something, and my other function takes what this function produces. So I'm always chaining things. I'm always solving something and chaining it to something else and so on. And you are kind of like a composer, kind of orchestrating what goes where and how things are kind of linked together. And this linking, this sort of mechanism of like linking things together has to become your second nature, because you have to do it well. You have to think what I am producing and what will be consumed. So it's always some form of chain of dependencies. So when we define our programs, we often say, okay, we consume something, we consume some parameters, and we produce something, and something else is going to consume what we are producing here and produce something new, and so on, right? In C and C++ in kind of imperative programming, we often use variables. So we say whatever this produces goes into this variable on this box, and then this thing is using this and so on. But in functional programming, we are much more tidy. We have to think more clearly what is produced, what is consumed, such that we can compose our programs in a more natural way. So that's what we're gonna talk today, and that's what I wanted to highlight. I didn't want to really talk about Oak. I wanted to talk about this pipe that I suddenly combined listing of folders in the like one tool with another tool, and I got something out of this. And we often do that. We often have a problem and we have to decompose it and say, okay, this problem is actually 5 different problems, and I have small solutions for all those 5, and I just need to combine it. All right, so enough of the rant. Let's go back to the plan and to the lecture. So first, the plan. Let's go back to the wiki. So as I said, we will have kind of busy 2 weeks, and then we'll have a little bit of a slack. So the next 2 obliques are kind of in a row. They are super easy, super simple, and you will have some activity in the class before. So this activity today is really helping you to do the task 03, and the activity next week in the class is also helping you to do this. You should submit the activities in the class at the end of the class. So again, if you are here and you've done something, submit it. We're not gonna use peer review for the activities in the class, but I want you to kind of submit it and take notes. That will be super useful at the end of the course for your portfolio. And then for the obliques, you kind of have to do them. Any questions about this? Yep.
In what way is it helpful for your portfolio?
Because you will have some commits in the repository, and you can use them in the portfolio, right? There is a pattern. It seems like the even numbers tasks are always done in the class, and the odd number tasks are always done at home. And it's a nice pattern, but it's a bit heavy. So I'm not sure if I will follow that we always have tasks which follow that pattern. Maybe sometimes we will have a task which is bigger and we start it in the class and then actually it carries over to home. So I'm just saying that maybe the pattern will be broken in the future, right? But currently the pattern is like this, that the even numbers are in class and odd numbers are at home. Okay, so there was a question early on, how will I get A? It's a hard question because I don't know exactly what you have to do to get A. Normally, I try to set it up in such a way that if you do everything I want, you will get A. But sometimes it's too hard and like not anyone gets like to do everything. And then sometimes it's like too easy and it's kind of hard. So I have this sort of proficiency notes, and if you check them, it kind of gives a feel of what is expected and where you're going with this course and where you're going with your programming. So I tried to organize it into kind of a complexity classes, and then try to specify what is fundamental and basic and what we will try to go beyond. But it's kind of hard for you to now kind of probably understand it. You will probably understand it much better towards the end of the course. So I will give you a bit of a flavor today because we will talk a little bit about loops. Yeah, but it is there. So it is there for reference. I also have this wiki page which defines the rules for the course. And if there are questions or if there are some things that you would like to be added or removed, then we can discuss it through the issue tracker. And also, as I notified through the email, we are gonna use issue tracker for announcements, and I will from now on sort of do them here. So if you want to be notified, you can sign up yourself to a particular label, and then you're gonna be notified when that label is posted, right? So you can kind of make your decision if you want to be checking it yourself or kind of subscribe to that label, and then you will see it. There are some let me quickly find where it is. Labels. So we have some labels for the course. So announcements, critical announcements or critical bugs, and then you can post feedback. And then we have some language specific tags. And then if there is something related to tasks, you can tag it with tasks. So you can use multiple tags for something like, Haskell related question about task 005, then you can kind of say Haskell task, okay? It's quite straightforward. Okay, so one more thing about GitLab. Not everything works as intended in GitLab. We don't know exactly why. GitLab is a little bit of a buggy software. So if you hit some walls, just make an issue or tell me through Discord or email that, oh yeah, I tried to do this and it didn't work. One thing that we tried yesterday with one of the students was that we have this course and you can, we have this course, so our course, and what you can do is you can fork it. What does it mean is that you're basically making a copy of this course and the repository in your own personal workspace, and then they are sort of linked. There is a relationship between the upstream and the kind of your fork. And that didn't work actually. Like normally it works, but like we really tried yesterday like 4 times and it didn't work. There is something not quite right. So he eventually set it up by hand. You can sort of by hand clone this project to your laptop, create a new project by hand, create an empty repository in your own project, and then push your clone to that project. And then you basically have this upstream, downstream relationship. But we had to do it by hand. So you can do it with Git, but GitLab sometimes it's a bit quirky. So if you notice that, fine. Like there is a lot of memes of how buggy and how insecure GitLab is. So we can kind of contribute with some fun observations. All right, any questions? No questions, then let's start Menti, and then I will start you some questions through the Menti. Man, it's 8:40 already. I talk too much. All right, so let's see. So about your Haskell setup. Great. So it looks most people are sorted. Those who are not yet, please get sorted today. So use the TAs and use your friends around you to kind of get yourself set up. We will I will encourage you to use command line and to sort of work with Haskell through command line initially. Once we get to bigger projects and multi-file projects, then you can start doing something in the IDE, in the integrated development environment. But initially, kind of try to build and do things in command line. It's much easier to debug, and it's much easier to understand what is working and it is what is not working. Okay, so next question. What are you planning to use in the course? So it's sort of a much more uniform distribution. So the people who are in the first two columns, Linux and Mac users, they will have it easy. And people who are in that column and maybe in that one will have it a little bit harder. So you will have to work a little bit more on some semantically not related issues. Right? So there is more to fiddle with. But it's okay. I talked with Christopher yesterday and he offered a lot of help to Windows people. He also said he is thinking about using PowerShell for some of his demonstrations about command line usage. And there is a Windows, the Linux subsystem. So maybe it will not be that bad. But the experience from previous years was that Windows is a little bit more annoying, so to say. Those two will be kind of fine. If you get really annoyed and you are on Windows, just use a VM. Use like VirtualBox or something. Set up yourself a Linux and use Linux. For those easy people, you can set up yourself a Windows box just to experience some things. I tried to do some Haskell development on Windows 2 or 3 years ago with some graphical libraries. Yeah, not easy. So, I mean, we are here to learn, so experiment. If you don't have a Mac, obviously you're not gonna try, but trying Linux and Windows, it's like for everybody, so you can sort of do it on a PC. All right, Git, so upstream and downstream. and the origin. So I hope you sort of understand the concepts and what is the origin, and you understand that Git is a distributed version control system. So it's not a client server that you are working locally on something and pushing to a server. It's like distributed, so everything is kind of equal. And we make the relationship like what we consider to be upstream and downstream, and we are the ones defining who owns the ground truth, right? So I encourage those who used Git for a while and are more familiar with Git to set up sort of things with your friends such that you have multiple remotes. You not only have the origin, which is in GitLab, but you have a remote, which is your friend, and then you can kind of pull and push between different remotes, and you sort of like get this nice feel that Git is truly distributed version control system, right? Things get messy, especially if you're working on projects and you do have this multiple remote situation, but it also is quite nice for pull requests and so on, right? So forking, that's what I discussed before, that forking the course project into your own workspace actually didn't work this year. It worked last year quite okay. This year it didn't work. So you may, if you want to do this, if you want to have this upstream downstream relationship, you may need to do it by hand. And then cloning to your laptop and then copying files to your workspace, cloning your workspace and making it sort of independent. Yeah, it's up to you. The advantage of having this course as a upstream from whatever you're doing is that there are brownie points for people spotting errors and mistakes in my slides and in the tasks and stuff on this wiki. But yeah, by the way, the wiki, let me show you. So this is a Git repository, obviously, so you can clone it. And then if you go to the wiki, wiki is also, so this one has, okay, let's copy that. So if I go away, clear. So if I paste this URL, there is a certain URL, and then the final thing is .git. If you use this URL and say .wiki.git, you're gonna get the Git repository of the wiki. So you can have both of the wiki as a Git repository and this repository. And then if you spot any errors or typos or mistakes, you can create a merge request and you can say, there is a error or there is a typo, and you can post it, and then you get brownie points, and those brownie points will count towards your grade later. So if you're looking for A or high, good grade, you should kind of try to spot mistakes or errors or typos, and then just fix them and make a merge request. But to do that, you have to have this repo as a upstream repo in your own repo to create a merge request, right? You cannot have kind of independent repo. So you do need to establish this relationship between your local repo and the upstream repo. So much talking. All right, so question about this? Everything I just said is clear to you, or you got lost, or if you're a little bit lost, that's fine. That's why we have this course. This course is to polish your Git skills and to get yourself like level up. If you already are fine with everything, then help the people who need a bit of help with Git. And for those who are completely lost, yeah, you do need to watch some tutorials, and you do need to get to talk with the TAs or with me and get yourself sorted with some basics. You don't have to do a lot of fancy things, but being kind of understanding the origin, like where you're pushing and pulling from, and understanding that the origin can have multiple, like you don't need a single origin. You can have single origin, but you can have another remotes, and you can push and pull from other remotes. That's a useful skill. So you should kind of know that. And then branching and committing and the commit space and so on. So the fundamentals. You don't have to know like cherry picking modules or very fancy kind of Git things, but the yeah, the basics we kind of expect you to sort of master here. And then, yeah, that's fine. So will, through those weekly commits and weekly work, we will kind of master some of the Git skills a bit better. So do you have any Git questions, Argent, right now? Yeah, maybe you ask the, like, after the lecture, like the TAs when you're working on the tasks. How about GitLab? GitLab can be a little bit confusing, and initially it's a little bit overwhelming because there is so many things. It's just that we don't use most of them. We don't use most of the stuff that is in GitLab. We only use the repositories, the issue tracker, and the wiki. Everything else we will use a little bit later, like the CI pipeline, because it's super useful for your third-year courses and for the bachelor. But we try to limit it. Like I think Tom is using some of the planning features and boards in next year. But this year, you don't really have to do that, like this agile development. So gradually explore GitLab and sort of get yourself familiar. Most of the tools on the market, like GitHub, what was yeah, there are some other kind of a project management tools which we used in the past. They are very similar. So once you know one of them, once you know GitLab, it's kind of easy to transition to other ones. They do differ in the mental model. So for example, in GitLab, a project is a repo, and that is sort of more natural relationship. In GitHub, it's not exactly the same. So then you need to change a little bit your mental model sometimes. All right, we skip that as well. So I already talked about it. So we have tasks this year. The tasks, some of them are obligatory, some are not. Some are done in the class, some are done at home. And then obligatory tasks have to be done by everybody. Group work is encouraged. So for everything, even at home, you are encouraged to work with groups. So you don't have to work individually on anything unless it is specified in the task that the task is individual. Then you have to work individually. But normally the default is that we do stuff in groups in the class and we do stuff in groups at home. But commits are always individual. So everything that you work on in your own home workspace, it's your work and you have to do it on the individual basis. All right, so Haskell, yes, finally, like 50 minutes after 8. So we are kind of and starting a journey into unknown. Haskell is a little bit of a like a how would I say it? It's like a long adventure. So you're not gonna conquer it this semester. It's a long-term sort of skill, but it teaches you a lot about programming and it will make you a better programmer, even if you're not gonna use Haskell commercially in your career. So you will have to forget a little bit what you know about programming for two reasons. So one reason is that Haskell has a very, very different syntax. So the syntax that you are familiar with, this sort of a C-like syntax from other programming languages, does not work in Haskell. So it's a completely different syntax. So you have to reset your brain, say, okay, whatever I know about programming languages syntax is out of the window. Like I have to start new. Okay, it is a little bit painful for some people, but the other reason is that when you're learning programming, you're thinking in terms of a programming language. So you think, how can I solve it in C, or how can I solve it in C++? What C++ gives me to solve the task, right? So when you're approaching a particular problem and you decided that you're gonna solve it in C++, your brain kind of works in C++ way. So you have vectors, you have variables, you have that, and so on, right? And that's, of course, necessary to code because you have to at the end of solving something, you actually have to express it. And because you chosen C++, you have to express it in the C++ language. But the way of thinking about problem in C++ limits the concepts and constructs of how you're solving it, right? So to give you an example, Golang is a very simple language. And in Golang, you basically have functions and a for loops and structs. You don't have anything else. Like it's like very, very simple way of thinking about things. And then if you were thinking about solving problems only in those three terms, you will limit your way of organizing how things can be solved. So we have to go beyond that. And going beyond that means you kind of abstracting away from the concrete language, and you're solving your problems in a very language independent way using all the vocabulary and all the constructs that you have to solve a given problem, right? So you don't think in terms of syntax, you think in terms of concepts. And that's kind of new. And it comes from your ability to think in multiple languages. So when you learned one language, there is no way you can do this because you only know one language, right? So people, let's say, who program in Python and only know Python, they cannot do this like expansion of concepts because they are limited to what Python offers them. Same with Java, same with C++, and so on. Once you learn more programming languages, and especially Haskell, your brain opens up a little bit and you say, oh yeah, I can see the limitations. I can see what Java cannot do for me. I can see what C++ cannot do for me, or what is very clunky. And then what you can do in particular language, that if the solution is very nice and elegant in a particular way, you can produce the machinery for the solution to be built this way in a language which doesn't have that facility, right? So let's say, to give you an example, if the most elegant way of solving something is using faults, and in particular language, like in Golang, you don't have a fault, you can make a fault for yourself. So you can say, I have a fault function which does this, and then I will use it because that gives me the most elegant solution, right? So if you have constraint to Golang, which does not have faults, you would never come up with this. But because you know about faults, then you can do this. And that's what we do. And that's when a lot of libraries and a lot of support happens, right? So people, for example, build reactive programming libraries to many programming languages because they don't natively support it. But a lot of problems are very elegantly solved using reactive programming. Therefore, you have libraries to give you the reactive programming in C++ or whatever languages they don't have it, right? So that's why we try to kind of reset ourselves this semester. Syntax and semantics. We sort of try to go beyond what we already have. So I will skip this. So what makes a programming language is the syntax, abstract syntax, because you have concrete syntax to actually express something, like how do I do assignment? Like by equality or by this, in Golang, you can do by this operator. So this is like a concrete syntax. But assignment, as a concept, is an abstract concept, right? And it can be expressed concretely by different syntaxes. So we are focusing on the abstract syntax more than the concrete syntax because this one depends on a particular language. This one is a more general concept, right? So we are focusing on the abstract syntax more here. And then the semantics relates to the abstract syntax, right? And then because of the language and because of the vocabulary and the constructs that the language has, there is a certain way of thinking about problems. And because we are abstracting away from programming languages, we kind of going meta, like we going kind of high level. So we are talking about abstractions, about nuances, and about elegance, and about how things work in this sort of abstract sense, much more than in the concrete sense. Added advantages that AIs are super good in the syntax. They are quite bad in the semantics. So if you ask semantic questions about some sort of concepts and constructs to AI, they will have no idea because they are trained on syntax, on actual concrete syntax. They do have a little bit of a generalization to the abstract syntax, but not too well, and not the way humans have. And they are really, really shared in semantics. And you will you will see it towards the end of this course, and maybe next year, you will see the limitations of AIs in terms of actually thinking about abstract concepts and abstract constructs. All right. So I already talked a little bit about some of the concepts that we are covering. So expressions and statements. It's a big deal. It makes a big difference. Variables, values, and types, and constants, and how, mutable variables, immutable variables, and so on. So like, for example, if you talk about assembly, you have memory locations, and values are stored in memory locations. So you have kind of a box, and that's where you store your stuff, right? And then you say, like, it's a memory location. That's all I have, right? On the lowest level. But then came like high level languages, and they say, actually, it's useful to talk about variables, and talk about variables that are constant, like they never change, about variables that are initiated in runtime or initiated at compile time, variables that are mutable, and so on. So we have a lot of nuance, right? Is that nuance on the lowest level? No, there is no nuance on the lowest level. On the lowest level, you have memory location, and that's it, right? All this nuance comes from us thinking how we treat that box. So it's the same with everything else. It's the same with statements and expressions and type systems and so on. Literals, it's quite interesting as well. In Haskell, literals are polymorphic. We're going to come back to that later. In many languages, they are not. And it's so annoying that you cannot express polymorphic things with literals. We come back to that later. And then functions and procedures. So the usual things, and then control structures, loops, and so on, right? So what is a loop? If you were to explain what loop is to a baby, right? What would you say in a sentence or in an expression?
Something happening over and over again.
Yeah?
Or set amount of time. Oh, we're supposed to write it.
Yeah, something happening over and over again. Exactly. A circle. Yeah. Something that comes around. You do the same thing over and over again. Exactly. So those are certain definitions. And then we have iterating or reiterating. Is iteration and looping the same thing? I don't think so. I don't think iterating over something and loop are the same thing. Why? Right, so let's go to this one. What is a loop?
What is a loop? Well, it's like a circle thingy. What do you mean, circle thingy? Sorry, what was the question again?
And it loops, right? So, oh, come on. So iteration and loops are not the same. Loop is something that loops back to the beginning, and it kind of goes over forever, the circle thingy, right? Iteration is something that you iterating over. So you have something to iterate over. So it has the beginning and the end, and you're kind of iterating over. So you're doing something in a kind of loop, but it has a very different kind of a feel and very different construct, right? So again, in assembly, we only have jumps, and we have unconditional jumps and conditional jumps. That's it. There is no concept of a loop or anything. It's just a jump. And then when we came up with programming languages, we thought, it's kind of interesting because sometimes we want to unconditionally keep jumping forever and we have a loop. And sometimes we want to iterate over something like numbers from 1 to 10, right? That's an iteration. So then we have iterators and we have loops. And in some programming languages, this kind of a loop abstract concept and iterator abstract concept express in a concrete syntax in a very same way using a for loop, right? So the perfect case is Golang, because in Golang you can say for brackets, that's a loop, right? That's a loop. And then I can say for and then have this iteration kind of construction. And suddenly it's not the loop anymore, it's an iterator, which iterates over my collection or list, right? So you can say, yeah, it's all the same. And no, it's not. It's very different and even have a different concrete syntax, right? So when we kind of thinking about this, we have to be precise and we have to be like, yeah, I really need iteration here, or I need a loop, right? We very rarely need a loop. Where would you need a loop? Where would you need kind of going over and over and over something? Sorry? Yeah, when you wait, like a busy mutex, right? So sometimes you have kind of a busy mutex where you kind of waiting forever. Or you have, let's say, interactive command line, like if I go to my shell, right? So what is the shell doing? So I type something, press enter. What then happens? I go back to my shell. I type something, like I'm in a loop, right? That is a perfect case for a loop. I'm doing something, I'm going back to my initial starting place. I'm doing something, I'm going back, right? So this is a loop. Is that iteration? No, not at all. There is no iteration here. It's a loop, right? Iteration is like for 1 to 10, do something. That's an iteration. Okay, so we kind of clarified. Yes. All right. So let's do the quiz. What happened? Come on, don't do that. Sorry. All right. Start quiz. Did you see the correct answer? Maybe. All right. So how old is Haskell? It's not too old, actually. So we talked a lot about 60s and 70s in the previous class. Now we're going back to 80s, so not that bad, right? We're progressing. So it has been developed sort of as a response to aerial developments. So in 70s, we had C and Smalltalk. So those are the kind of three main branches of family of languages. So we have the C family of languages, which kind of came directly from assembly. We have a Smalltalk, which was much more abstract, and Smalltalk is one of those properly object-oriented languages. So if you were to really learn object orientation and object-oriented language, you would need to go to Smalltalk. And then we had those more math-based, more functional and lambda calculus-derived languages, which was ML. So we have those three main trunks in 70s. And then they evolved. So people noticed that, whoa, Smalltalk had so very nice features that they were so useful. Let's merge it with C and create Objective-C, right? So C++ and Objective-C were sort of additions to marry that trunk with Smalltalk. And then we had Miranda and Haskell as a response to this one. This one was a commercial language, and then Haskell was the open source academic response to this trunk. And then we had some scripting languages like Python, and then some merges like going from functional to the imperative. So OCaml is a very nice example of how to marry functional concepts with imperative programming. And then we have modern languages. So modern languages like Golang and Rust came in late 2000s, and those are the youngest and ones you are learning now as well. And Go goes all the way to C, and Rust kind of tries again to marry imperative C-like manual memory management with functional flavor and functional concepts. So Rust is sort of again marrying those two trunks, the C and ML. Golang does not marry too much. It is mostly a descendant of C, trying to strip it from manual memory management and introduce some modern features. And then we have C#, which is sort of the response of Microsoft to Java dominance, and F#, which is it's actually one of the most paying programming languages. So if you check which programming language jobs have the highest salary, it's F#. And F# is basically .NET with functional programming. It's like Haskell on .NET, right? So it has very similar syntax, and it is basically functional programming on .NET platform. All right, so there was a need for an open language, for an open source language, which was shared across research community. And the latest standard that we are using is from 2010. Okay, last quiz question. We don't have many quiz questions today, which is good. So let's see. So what is Haskell? Is it lazy and compiled, purely functional, statically typed? Does it have type inference? Is it concise? Does it have a garbage collector? Which of them are true? So all of them are true. So it is a lazy language. We will talk about laziness later. It is compiled to the native platform. It's not interpreted. It's purely functional, as functional as you can get. Golang is often said, yeah, it's an imperative, but it has a functional flavor because functions are first order citizens, which is true. And you also feel in Golang that there is a lot of higher order functionality. Like you have a function to, you didn't probably talk about it yet, but when you're installing your web server services endpoints, you have a function which kind of initializes that. And then you're putting functions as parameters to callbacks to which routes will be handled by which functions, right? That is a kind of what we typically do with functional programming languages. We're passing functions around. And then it's statically typed. So not like Python, where type is inferred, or not like Oak. Oak is another example of dynamically typed language. JavaScript is another one. It has type inference, which means you don't have to say what type things are, even though they have type always. It's very concise and it annoys a lot of students. And it has a garbage collector, which again limits what you can do in terms of controlling the memory and controlling the speed of your execution. But Golang is the same, right? So one of the manually managed languages that you already know, or two, is C and C++. And one which you will learn now is Rust. So they don't have garbage collector, and you have to manage memory yourself. But you say, oh, wait a minute, but I say make in Golang, like I'm making kind of structures myself and I'm allocating memory, right? Yes, you do, but you don't free it. Like managing it, freeing it, and garbage collecting it is done for you. You don't have to think about it. How about Rust? Yes, it is done for you as well, but in Rust, it is done at compile time. So at compile time, Rust checks where you're creating stuff and where things needs to be disposed, and it is doing it at the compile time. In C++, it's a bit of a mixture. Some things are done at compile time, and some things are done at runtime, because you can allocate some of the pointers as being tracked, and the system will kind of do it for you. So modern C++ has a little bit of like automatic garbage collector with reference counting built in into the runtime system. All right, so we almost there. Sandelmo, the winner. So another thing that we have to switch gears a little bit for this course is that we are very used to imperative programming. We like telling computer what to do, which comes from assembly, right? So this branch, which I told you earlier about, the branch of C, it comes from like assembly programming, where we were directly instructing computer what needs to be done. And this branch is a little bit different, because this one says in a more abstract sense, same as this one, what needs to happen. And often the distinction is between telling directly what needs to happen in which sequence versus declaring what things are, and then things happen because of what things are. So in Haskell, we often do this. And there is an imperative syntax, an imperative mode, but it is not the same as in imperative programming languages. In imperative programming languages, the order is always important. Like if I have code and I said this, it means this gonna happen first, this gonna happen second, and this gonna happen third. But in Haskell, if I do this, it doesn't matter in which order I do them, because it is sort of almost always the same. The order often does not matter. I'm just saying, oh, those three things needs to be done. And then in which order is not as important as in imperative programming. Sometimes it is. So there are some structures where the order matters as well, but we are ordering things slightly differently than just by lines of code. All right, so it is lazy, which means we don't evaluate everything on the spot. It is statically typed, which means there is no type change of variables, purely functional and concise. Yeah, question?
Can we get a break?
Yeah, we can have a break. Yeah, let's have a break. So 10 minutes. 8 minutes. Fun things. So we have to start with Hello World. So you will start generating a Hello World application. And then you will play with the some of the tools, right? So one of the tools that you are probably familiar is the GHC app, which is the manager. This is the compiler. You're not gonna be invoking the compiler manually unless you're really doing something hardcore. You will be invoking the compiler through stack and saying stack run, stack build, and so on. That is much more convenient. And then there is this GHCI command, which helps you with, let me show you. So if you go to GHCI, it invokes an interactive interpreter in your command line, and you can interact with it. It tells you which version of Haskell you are using, and then you can kind of interact with it. You can copy and paste some single lines of your code and check what happens, right? So we can define a function like add, which takes 2 parameters and returns the sum, right? So I just defined a function add, given 2 parameters, returns the sum, and I can say add 10, 20, and it will return 30. So I can sort of already play with Haskell in kind of interactive way, but it's easier to use an editor and edit your code and then do like import the code here and play with your functions inside this GHCI. The most important things is the I, which tells you the information about something. So if you don't know, put string line, it's a function in Haskell, and asking will tell you about what it is and where it is and what type it has. And also you can ask about type of things. So I can ask, what is the type of my add function? And it tells me, okay, it takes 2 parameters of type number. It's a meta type, so it's like a type class. So we don't know what is it a float or is it an integer? It is kind of generic, and it returns the same generic response. So I can say add 1 and 2, and it works with ints. And I can say add 1 to 1.2.3, and it works with floats as well. It's a generic function, right? I defined it once, and it by definition, it's generic. In other programming languages, we often have to make extra big deal about being generic. In Haskell, it's like the default is you are generic. Anyway, the point is about GHCI. Make GHCI your friend, because you can go. So to quit, you say quit. If you have a Haskell project, and inside that Haskell project, if you say stack GHCI, you will invoke for that project GHCI, which will load all the functions that you have in your project. And then in GHCI, you can play with them. You can call them, you can pass parameters, and so on. So it's kind of a useful thing to know. Another one is Hugel. You will use Hugel a lot as well. And it basically is, if you just go Hugel, it goes to hugel.haskell.org, and it's basically a search engine for Haskell. So you can say put string line, and then you have what it is, where it is placed, and then tells you what that function is. So if I go there, it sort of tells me a little bit about what it is. Sometimes it tells me some examples, how it is used. So like here we have some examples of how things are used and so on. So Hugel is your friend for learning about some of the functions and types in Haskell. You should prioritize using GHCI and Hugel for all the tasks which say don't use AI. So don't ask AI for things, use GHCI and Hugel for things. When the task says use AI, then of course you can also use GHCI and Hugel, but for explanations or for demonstrations, you can go to AI. But for the very basic things, go to those resources. It will show you the ground truth. It does not hallucinate, it does not make mistakes, and it gives you exactly what you need to know. Okay, about the IDE, as I said, I prefer if you use something very small, maybe Visual Studio Code, or maybe Vim or NeoVim, or something small initially. And then for larger projects, you can go to Visual Studio Code on IntelliJ. But for the very simple programming, try to go minimalistic. Syntax highlighting, of course, is nice. Some completions is nice, but try not to use it initially. Use Notepad or like Vim or something. Should you learn Vim or NeoVim? I think so. So I think you should learn how to navigate Vim motions, because they help you later with a lot of different tools. And even if you're using IntelliJ or Visual Studio Code, you can still enable Vim motions and use Vim motions in the much more robust and complicated integrated development environments. Will I have it in the exam? I am still like contemplating. So I haven't decided yet whether Vim and NeoVim will be required in the course. Definitely you don't need it to pass the course. But to get A, maybe I will require one of those Vim motion editors. I haven't decided yet. We can vote on the idea in issue tracker maybe. All right, so functions. Super simple, but at the same time, a little bit confusing initially. So we have to, like, each function has a type. So what does it mean that the function has a type? The same as in Golang or in other programming languages, it says what parameters the function takes and what parameters the function returns. What is the type, right? So if I have a func in Golang and I say it takes an int, it takes 2 ints and it produces an int, this is my type of my function, right? That it is so if I have something f and I say what is f, so f is a function which takes 2 ints and produces an int. It's exactly the same in Haskell, and in Haskell the notation is a little bit off-putting maybe for some people. So again, if I go to GHCI and I have my add function which takes 2 things and produces the sum, and then I ask what is the type what is the type of add? It says add, so it has this kind of notation of saying add is by this double semicolon or colon characters, and then we have traits with this double arrow, and then we have the type variables of my function. But to make it a little bit easier, let's say I have 2 ints which produce an int, right? So that's a kind of a simpler declaration which says add takes 2 ints and produces an int. You will say, so in normal C-like programming languages, we say func, and then we say int, and then we say int. And it's clearly different than those 2 things are parameters, and the last thing is the output, right? But in Haskell, you say, why it is sort of like, why we not differentiating between the first 2 and the last one, like we do in the normal programming languages, is because there is no difference actually. And in Haskell, all functions are carried, which sort of internally means all functions in Haskell take 1 parameter. But you say, no, wait a minute, Mariusz, that's not true. Like add takes 2 parameters. It takes A and B and produces the sum. And it is kind of looks like it, but inside it isn't. What add is add is a function which takes 1 parameter. It only takes A. And it produces a function which takes 1 parameter, which is the B. And that one, the second one, produces a function which produces a sum of the first A and the second B as a result. So it's a little bit complicated. You don't need to like master it yet, but you just need to remember that in Haskell, I can do very trivially things that are a little bit harder in other programming languages. So I can say f is add 10, okay? And now f is a function which takes how many parameters? Just 1, because it is kind of like add, but it is missing the second parameter, right? So I can say f2 or f3, and now I will have 10 plus 3, so it will be 13, right? So I now defined a function f, which is a carried version of add, which already has the first parameter set in, right? Can you do it in other programming languages? Yes, of course you can. I can declare like a function which takes 2 parameters and returns a function which takes only 1, which is the second one of this one, right? And I can do it. It's just the syntax gets really kind of clunky. In Haskell, the syntax is like super trivial to do those things. So how many parameters add takes? Well, again, if we ask about the type of add, so let's do add a little bit differently. So let me do int, and int. Yeah, I cannot really declare types in the GHCI, but if I say yeah, anyway, so if I do this and you see a list of things, you always look at the last one, which is the output, and the sequence of how many parameters the function has is the sequence preceding the last one, right? So the last one was always the last thing, the output, and the intermediate ones are the ones which kind of come along. So this is the type of the function. This is the type of the function, and then add equals, or add AB equals A plus B. This is the body of the function. This is the definition, right? So this is the declaration. This is the definition. So we have the function type, definition, declaration, and then arguments, and then application. Application is what we do when we apply a function to something, right? So if I have my func add, or even in Golang, I can say f equals func, and then I don't have to have a name, right? I can declare, I can sort of do this, and then f is my adder. I can say, it takes int a, int b, and then return a plus b, right? And this returns an int, something like this, and then I can call it. So this is my declaration and definition, because I declare the type and the body, and now I can apply it, and by saying, okay, I'm applying it by calling f with those arguments, right? And in Haskell is the same, as just we don't use brackets and we don't use the commas. So it's kind of the same. It's just the syntax is much more stripped. So we, instead of beautifying it with brackets and commas, we say, screw it, like it's just space, okay? So space is the function application. So here I have a function which is applied to two arguments, and the arguments follow, right? We do use brackets sometimes, because what if I want, if I have my adder, so if I do add 1 plus 2, it's the same. But what if I say add 1 plus 1 first? I want to say add 1 plus 1 to get 2, and then add the result of this to this one, right? I want to pass. So in Golang, you would say, or other C languages, you would say this, right? That would be the syntax. In Haskell, there are two ways of doing it. You can either say, okay, do that first. So do this first because it's in brackets, and then the result of this will be passed as argument to the first add. Or we have another syntax which says, do this, and whatever that is, pass it as an argument to what is on the left-hand side. So this is like an operator which says, do what's my right-hand side first, and then whatever is there, attach it to my left-hand side and use it as an argument. So this is a function, right? And you can ask about it. You can ask about what is the dollar, because it's like a normal function in Haskell. So you can say, okay, tell me about the dollar. And it tells you, okay, dollar takes a function on the left-hand side and an argument on the right-hand side, and then it will kind of evaluate the right-hand side first and give this one to the left-hand side function. So the left-hand side function is a function which expects one argument, and then whatever is on the right-hand side is given to the left-hand side. Again, don't worry about it yet. It's a little bit confusing. We will dive into that a little bit later. The point is, the syntax is that you have a name of a function, space, and arguments, right? So That's all you need to remember for now. And then if you need to pass arguments, if you need to pass 2 arguments, but the second argument you need to call a function, you kind of do it like this, right? All right. Composition. So imagine that I have 2 functions, and so let's say I have the function which so let's create at 10. So at 10 takes a and says 10 plus a, okay? So I have one function which adds 10 to a number, right? So I can say add 10 to 20 and I will get 30, okay? And then I have another function which multiplies things by 2. So I will have a multiplied by 2. So now I have 2 functions, one which adds 10 and the other one which multiplies, right? So then in Golang we could have 2 functions the same way. And now if I have a task is to to add 10 and then multiply by 2 a number x, right? So now I have x and I want to add 10 to it and then multiply it by 2, okay? So how would you do it? And let's say x is 3, okay? So you would say add 10 to 3, and then I have to multiply it by 2, right? So that's how I would do it in Haskell. And then in multiply by 2 at 10, 3. That's what you would do in Golang, right? It's exactly the same. Syntax is a little bit different. I'm not using those brackets. I'm using just the bracket to say do this first and then pass the argument to this one, right? Up to now, the 2 languages are exactly the same, but now the task is not to do 3, but to do a function which does this, right? I need to declare a function which does this, right? So, okay. So I will delete those brackets and I will use dot and I will say f. Now I have function f. So if I put f3, I will add 10 and multiply it by 2. So I'll get 26. And I created a function. I composed a new function out of the existing 2 functions. And the function composition in Haskell is by dot. So by dot, you're saying, do whatever you need to do here first, and then pass the result of this one to this function on the left. So again, if you ask what is a dot, again, it's a function which composes the functions for you, right? In Golang, you would have to say there is a function f, which takes 1 argument, which is an int, and then I would have to do the logic, right? It's a little bit more syntaxy, like it's a little bit like a lot of boilerplate to achieve it. But in Haskell, it's very concise. So if you need to compose 2 functions together, you just use a dot, right? So that's the function composition. All right. Basic types, we have ints, we have floats, we have bools, we have tuples, structs, and so on. We start with basic, like numbers and strings. And then we have lists. Lists are very common in Haskell, and they are defined like my list equals, and then you put what is inside the list into square brackets. So if the list is empty, it's it's an empty list. If the list has something, like let's say list has 2 numbers, you just do this, and then you can say what is the length of the list, and it tells you I have 2 elements. So lists is a very common data structure in Haskell. Can I mix types? Can I have a number and a string? What do you think? No. Why? Because what would be the type of list like this? It would be like awkward. It's a type of stuff which does not have a type because we don't know what the type is. So it would not be strictly typed, right? Haskell is strictly typed, and lists like that cannot happen. So it's like an error. But what, like you say, yeah, Mariusz, but I need a name and the age, and I need to represent it. Then you can use a tuple. So tuples are fine with multiple things of different types, right? So if I say L is number and string, and I ask what is the type of L, it will say, okay, type of L is a tuple of two things. One is a number. We don't know, is it a float or int? And another one is a string. What if I say, actually, it was a float, right? Then it says, it's a fractional. It doesn't tell me it's a float. It tells me it's a fractional number because it has decimal places. And then it's a generic type. So floats have different types, as we learned from task 1. So we're using kind of a generic stuff here. What if I have my list of two things that are both strings? And I ask, what is the type of L now? It says, yeah, it's a list of strings, right? Okay, so then you have head and tail, which is a concept of lists. So if I have a list of, so again, let's quit that. Let's clear this and let's go to the top again. So if I have a list, which has first, second, and third. Okay, so now I have a list of three things. The length is 3. And then if I say, give me a head of L, it will give me the first element. It will right, so it gives me a warning saying, look, if you call head on an empty list, we're gonna throw an exception, which is nice, but I don't kind of care at the moment. And then it gives me the first element, right? So if I say tail of L, it will be everything which is left after the head. So because I have first and 2 elements, it will give me second and third. So it gives me second and third. But if I had a list which is just 1 element, and I say head of L, it gives me that first element. But if I say L odd tail of L, then after the first element, there is nothing. So I'm gonna get an empty list, right? So head, tail, length, concatenation of 2 lists, and then append. So concatenation is like I have 2 lists. So I have L1, which is just 1, and I have L2, which is 2, 2, and 3. And then I can say, what is L1 concatenated with L2? And it's like 1, 2, 3, right? So it kind of concatenates the lists. Can I concatenate, can concatenate 0? So I say 0 plus plus L1 plus L2. No, you cannot, because 0 is not a list. But if I put 0 into the list, then I can, and I have my list from 0, right? So what if you want to concatenate something to a list, but it is an item, it's not a list yet? Then that's what you would use, right? So if I have 1 and append it with this colon operator, then I have 0, 1. So you pretty much now know everything about lists and a null function. So if I say is L1 empty, it says false, it's not empty. is an empty list empty? Yes, it is. And then if L is an empty list and I ask, is L empty? It will say true, right? So there is a little bit more to lists, but this is all you need to start with. List comprehension. This gives students some headache. It's a little bit like those of you who know Pascal, Python. It is the concept is kind of familiar, but it is a little bit. Let me clear this and start from the top again. So this is a list, right? It's an empty list. If I need to generate numbers from 1 to 3, I can type them, right? But if I were to generate a list of from 1 to 100, that would be a lot of typing. So there must be a better way, right? So the better way is so-called list comprehension. A list comprehension is a mechanism for generating lists on the spot using literal notation in such a way that I don't have to type too much. So one way is you can say it's a list from 1 to 100, and you just say dots, right? And that list is a syntactic sugar for me typing from 1 to 100, right? They are exactly the same. So now I can do more tricks with it because I can say, okay, I have a list from 1 to 100, which I will assign to X. And now I can, for example, say to X. And now let's do up to 10, so it's a little bit easier to see. And now I will generate a new list, which is doubles from 2 to 10, right? So what do we expect? We expect 2, 4, 6, 8, 10, and so on, right? So a list comprehension is this sort of a notation where I have like what to do with some placeholder, with some variable, and then how to generate the variables, right? It's a very nice syntax, especially if you need to do some permutations or some more complex things. So for example, if you say, I want to generate tuples, which X is from 1 to 10 and Y is, for example, true and false. So we can say it's true, false, right? So now I'm generating all possible tuples between 1 and 10 and true and false. So I have 1 true, 1 false, 2 true, 2 false, and blah, 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 right? So this is a very nice, concise notation for generating lists. The concept of generating lists might be new to you. So if you never use Python or if you never generated lists, like using some form of list comprehension, the concept is new, but it's super useful. It's very useful when solving things to be able to generate lists on the spot and use them for some sort of partial solution. So you will have to practice that a little bit to get your head around. And then it often replaces the need for any loop or iterations. You see, like I didn't use any looping or any sort of concept of loop, but this concept of this arrow going from some sort of container into a variable, it is sort of reminds you of the iterators, right? Over a particular collection. So here I have a collection, which is a list from 1 to 10, and then I'm doing something over that collection with this assignment, with this kind of X. All right. So then I have a number of useful functions for lists. So like sums, if the list has numbers, sum gives you the sum of the numbers. Product gives you the product of all the numbers. Takes numbers. So what happens if I say I have an infinite list? So A is an infinite list. It goes from 1 to infinity, right? Can you do that in C++? Can you say, I have this list from 1 to infinity? No, you cannot, right? So because C++ is not lazy. You can do it in lazy languages because they don't evaluate A yet. They will evaluate A when it's needed. So now I can say, okay, take 10 first elements from A, and it basically takes the first 10 elements of A. So it's from 1 to 10, right? Even though A goes all the way to infinity, I can process only the first 10 elements. So take, and then the number and how many you want to take from the list, right? Drop is like we want to drop the first 10, right? So if I say B equals drop 10 from A, now I have a new list which goes from 11 to infinity called B. And if I say take me the first two numbers from B, I will have 11 and 12, right? And then maximum minimum. What will happen if I call maximum on B? It will kind of hang, right? Or throw. Let's see. It will hang. Okay, so let's not wait. But what will happen if I say minimum? Minimum. What's minimum of B? What's B? Okay, what is A? A is a list from 1 to infinity, right? So what's minimum in A? 1, right? So if I do that, it should give me 1. But because the list is infinite, it kind of tries to find what's minimum, and it's never going to finish because it goes to infinity, so it's going to hang, right? So even though the list is consecutively growing, it doesn't know that it's growing, so it doesn't know how to calculate the minimum. It treats it as a list, which is infinite. So we cannot do that. But if I say minimum of take 2 from A, and now I'm taking 1 and 2, it will know it's 1, right? So the laziness sometimes bite your ass, because sometimes laziness works fine. And it, like here, we kind of are working fine with infinite list, and we get a result. But with this one, we will not get a result because it kind of never know what the minimum is. So you kind of need to think when you're taking advantage of the lazy features of Haskell, like whether it will finish or not. Okay, so I will finish here. So write a list comprehension that produces squares of odd numbers from 1 to 11, right? So we have to produce squares. So let's do it together. Let's quit this, clear this, and start on the top again. So we need to produce a list, so we know we're gonna use a list comprehension. So write a list comprehension that produces squares of odd numbers from 1 to 11. Okay, so we need to make the squares. So to square a number is to multiply it by itself. And then we need to have numbers from 1 to 11, right? So we have x's which go from 1 to 11. And they need to be odd. So we need a condition now. So if we did that, we're gonna get squares of numbers from 1 to 11, right? Yeah, but we want 1, 3, 5, right? We don't want 1, 2, 3, 4. We want only 1, 3. So we need to add a condition. How you add conditions? By comma. So by comma, you're saying some logical expression that needs to be true. So for example, I can say x is bigger than 5, and it will only do for 6, 7, 8, right? So now square of 6 is 36, square of 7 is 49, square of 8 is 64, right? But you can also say, okay, I want the numbers to be odd. So odd x's. Odd is a function which returns true if the number is odd. So now it works. It's 1, 3, 5, right? And the square of 1 is 1, square of 3 is 9, square of 5 is 25. Okay, so I will finish here, and then I will let you play for the remainder of the time, which is 2 hours, with the task 03 and no, 02. 03 is a homework. And submit how far you get. The task 02 is very simple. It's just like doing a little bit of Haskell and kind of inline. It has some skeleton code embedded. There is one extra thing that I need to tell you. So the one extra thing is that Haskell has 2 file formats. Many programming languages these days actually support something similar. So if we go to task 02, if we go to this one, you will generate the code yourself, and in this one you have the code generated, and the code is, so normally the Haskell code is inside .hs, and then .lhs is literate Haskell. So LHS is a text file, which is basically like Markdown in our case. And then when you want Haskell code to be embedded, you use this bigger than symbol, and then you write your code. So all this text will be ignored when you run Haskell on this file, and Haskell will only use the lines which are with this, right? So for heavily documentation-based files, that's an alternative way of doing something, because the code is sort of visible as this, but all the text doesn't, it's like a normal markdown, right? It's like just a text. If you do .hs, it's other way around. You have to make text to be comments, and then the code is just normal text, right? Do you get it? A very trivial kind of use case. And for the first 2 tasks, I kind of played with the literate Haskell notation, which is this, and then if you use that file, it will work fine, but effectively it is just a text file, right? And the code is kind of embedded like this. So the code looks like a comment, and the text looks like a normal text. And then if you go, let's say we go to the heavily documented task 5, So if we go here and we go to some generated project and go here, we have .hs, and it's a normal Haskell file. And then we have to comment all the text with the --. So all of this is comments, and then the normal code is just code, right? So remember whether you're using .lhs or hs files. All right, so I stop here, stop recording, and then we're gonna try to do as much from task 2 as we can.